As you see, the concept of a regular expression is a very powerful one, and we can describe a lot of sets of strings using regular expressions. This might lead you to think that can we express any set of strings, binary strings or otherwise, using regular expressions? And the answer is unfortunately no. For instance, consider the set of binary strings that start with a bunch of zeros and then are followed with the same number of ones. Okay, so this is like, well, lambda is included here because n can be 0, or 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and so on. The question is there a regular expression to express this set of strings? Now, let's assume there is. Assume that this set is regular. Then, this means there is a finite automaton by Kleen's theorem. There is a finite automaton recognizing this set, okay? And again, remember, this is a finite automaton, so it has finitely many states. Let's assume the number of those is n. And since n is a non-zero integer, right, the automaton should recognize the string 0 to n, 1 to n, meaning that you have n zeros followed by n ones. Now, consider the states that the automaton passes through while recognizing the input 0 to n, 1 to n. Let's say these are S0, the initial state, followed by 2n states, right, in recognizing this string, because we have assumed that it should be recognized by this automaton. Now, consider the first n plus 1 states, S0, S1, up to Sn. Now, Sn is the state we reach after the last 0, before the very first 1. That is the state we reach. So S0 through Sn. Now, there are n plus 1 states here. And by the pigeonhole principle, recall, since the number of states is n, and I have n plus 1 states in the sequence, at least a pair in the sequence must be the same. So I must have a repeated state here in this list. Assume that those are Si and Sj, and I and j are between 0 and n, obviously inclusive, but assume that I is less than j. This is strict inequality here, I less than j and not equal. That is essentially due to the pigeonhole principle. We have established that at least 2 different states here must be identical, because we have n plus 1 states in this sequence, but the total number of states is n. So this means there is a loop from Si to itself, which is Sj, of length j minus I. So you have S0, S1, and with all zeros, you end up with Si. And there is a loop to itself, because at step number j, you are also at Si, and then you continue to Sj plus 1 and up to Sn. Okay, so this means there is a loop of length j minus I, and j minus I here is not 0, it's positive. Now, consider the string 0 to n plus j minus I, 1 to n. So this means you have n plus j minus I zeros, followed by n ones. Now, this doesn't fit the description given here, 0 to n, 1 to n, because it doesn't have the same number of zeros as ones. So it should not be recognized by the finite automaton recognizing this language here. However, since I have a loop from Si to itself of exactly j minus I length, this string will also be accepted, because when I hit Si, I'm going to take a loop of j minus I, and due to this excess j minus I, I'm going to take another loop, loop here from Si to itself, and then continue the transitions, which will follow the same exact path that the input 0 to n, 1 to n caused. So the result will be an accepting state, which means this string, which is not in this form, is going to be accepted by this finite automaton, which leads to a contradiction. Therefore, this cannot be a regular expression. It cannot be a regular language. Alternatively, we can say that there can be no deterministic finite automaton or non-deterministic finite automaton that recognizes such a language. That is due to the fact that the finite automaton has no infinite memory, because n here, the number of zeros or the number of ones, can be arbitrarily large. So for the recognition of such a string, you have to remember how many zeros you encountered. And you cannot really set aside a different state for counting the zeros, because however many states you define, there can be a longer string that your machine will be unable to recognize. Okay, therefore, the fact that your finite state automata has memory embedded only in the states, and the number of states is finite, such a language cannot be recognized by a finite state automaton. Therefore, this is not a regular language. So what to do? How are we going to actually recognize such languages? To recognize such a language, we have what we call a pushdown automaton. Now here, the difference from the finite state machine or the finite automaton is it includes everything in a finite automaton as well as a stack with unlimited memory. Now you have a separate memory unit apart from your states. You have a stack, so you can push and pop values to your stack, and essentially the capacity of the stack is not limited. So that is how you come up with a structure that can recognize such languages. So what are you going to do? As long as you encounter zeros, you are going to push them to the stack. And when you start seeing the ones, as soon as you encounter a one, you pop one of the zeros. With another one, you pop another zero. With another one, pop another zero. Of course, along the way, if the pattern is spoiled, then you give up and do not accept. But if you reach the end of the string and you encounter the final one, which matches the end of the stack, which you pop the final zero, then you know that the number of zeros and the number of ones would be equal. So that is how you recognize the string 0 to n, 1 to n using a pushdown automaton. And such languages we call context-free languages. These are a broader category than regular languages, and they require machinery further than finite state automata. But these are not the exhaustive, let's say, exhaustive category of languages. We have, for instance, if you have 0 to n, 1 to n, 2 to n, let's say you have an alphabet of 3 symbols, 0, 1, 2, and using a pushdown automaton, it is not possible to recognize such a language. I'm not going to go into the details, but essentially you can show that such a set is not a context-free language, but it's a context-sensitive language, because the number of ones depends on how many zeros you encountered before and how many twos you will encounter later on. So this is what we call a context-sensitive language. To be able to recognize such languages, we need linear bounded automata. Okay, so this is a more general structure than the pushdown automata. And again, I'm not going to go into the details of this, but these are important concepts when designing programming languages, essentially. And again, furthermore, context-sensitive languages, again, are not the most general case. The most general case in the theory of computation is for language recognition, the most general automaton is the Turing machine. A Turing machine is a finite automaton along with a tape. So you have a memory that you can read and write, and it has infinite capacity, and you can access it sequentially. So you have a tape, potentially with data on it when you start your program. So that is the string, let's say, to be recognized or rejected. And the tape can move towards right or left so that you access every symbol, and you can modify whatever is written on the tape depending on your state and the symbol on the tape. You switch your state and you modify, you possibly modify, you don't need to, but you can modify the symbol at the current position in the tape, and then you move one position towards right or towards left. So that's essentially what we call a Turing machine, and it is the most general computational tool in the context of theory of computation. And these languages, they define a hierarchy, as you have seen. The type 0 grammars are unrestricted, and we call these recursively enumerable languages. And this is an important concept in mathematics also. We have the concept of recursively enumerable functions. And these are recognized by a Turing machine. It's possible to prove this. And if you go one step further in special considerations, you have type 1 grammars. These are context-sensitive grammars. And context-sensitive languages are recognized by, again, the linear bounded automata. And these are special types of Turing machines. You have, again, the entire concept of the finite state automata as well as the tape. So you can modify the contents, but the length of the tape is not infinite. But for context-sensitive languages, it is sufficient to have an integer multiple of the length of the input. And type 2 grammars we are going towards from general to special. These are context-free grammars, and context-free languages are recognized by pushdown automata. Remember, this is a finite state automaton plus a stack, which is infinite. And finally, type 3 grammars are called regular grammars. These are regular languages, and they are recognized by finite automata. So type 0 grammars is a superset of type 1, which is a superset of type 2, which is a superset of type 3, which are regular languages. And this hierarchy was defined by the famous American linguist and philosopher Noam Chomsky.